start. So, Yash, thank you very much. Yeah, actually, we met at a conference. It was very nice to talk with you. It was on the related subject. So today I'm going to introduce Yash Vardhan Pant, professor of electrical computer engineering, University of Waterloo. And he will present work on signal temporal logic objectives, which is something that a couple of us at the school kind of think and work on, kind of try to do something in that area. So, and we will, yeah, we're really glad that we have you today to give us your seminar. So yeah, time is yours. Thank you.
Thank you, Rajan. Thank you for the introduction, and yeah, thank you to the organizers for inviting me and for Eric for making sure everything is running smoothly, at least until now.
Yeah.
So yeah, my name is Yash Pant. I'm an assistant professor in electrical and computer engineering. Today I'll talk about, I guess, a series of works of mine which focus on motion planning for multi-agent systems with complex objectives given to them as signal temporal logic specifications that have to be satisfied. Before I dive into the topic, right, a quick overview of what my group does. So I started at Waterloo in July 2021. I run what we call the Control, Logic, and Learning Group. And we're mostly interested in safe decision-making for autonomous systems in the wild. So dealing with multi-robot and autonomous systems and control theory for that is one of the main things that we do. These robots, of course, are not operating in isolation. They have to work around humans and work with humans. So we're also interested in problems of human-robot interaction. And I've also done some work on the problem of assurance of safety of systems that have black box, mostly data-driven components in the decision-making loop. So that's another theme. And as the name of the group suggests, the main tools that we use are control theory, a little bit of machine learning, and elements of formal methods, mostly temporal logics, so which is kind of going to be the focus of today's talk. By the way, feel free to interrupt me if you have any questions. I have a lot of slides. I don't need to go through all of them. So if you have questions that are burning, just feel free to ask me to stop. Right. So yeah, for today's problem of motion planning with complex specifications, the motivating problem is that of urban air mobility, or this near futuristic scenario where we'll have a wide variety of manned and unmanned aerial vehicles carrying out many missions in dense urban airspaces with a lot of rules on how they operate. The goal of this series of works is to then develop, essentially come up with robust and scalable motion planning and control schemes for multi-unmanned aircraft systems carrying out these unmanned air mobility type of missions. I won't focus too much on the application side. I guess I'll go more into the underlying methods. So, but there's a lot of work on the application side in this as well, which I'd be more than interested to talk about. Before I dive into the technical details, it's worth showing an example of one of these methods in action. Over here, we have 4 crazy fly aerial robots. Think of them as being in teams of 2 each. Red and blue are one team, green and black are another team. And they're tasked with this mission that has requirements in space, time, and even across agents. So in the first 6 seconds, these robots have to visit these virtual goal sets, which are shown in green. In the next 6 seconds, the team should be in the opposing goal set, and they should repeat the process twice. They need to do this while making sure not to fly into this virtual no-fly zone, which is kind of given by where the coordinate axis for this workspace is defined. And these drones should also, of course, not crash into each other or fly outside of this motion capture area. So all of these type of requirements can be very naturally encoded using signal temporal logic. And we'll take a look at a few examples of that. And what our method does is essentially generate trajectories. And one of our methods will also synthesize controllers that can track these trajectories such that they satisfy these specifications robustly. So on the top right, we have a simulation. And on the main screen, we have an experiment. So we see that in the first 6 seconds, both robots from each team make it inside their goal sets. Then they head to the opposing goal set. They're going to fly around, repeating this process twice while making sure not to crash into each other. One thing worth noting is that what's happening in the simulation is exactly what's happening in the experiment as well. That is because we have strong guarantees on kinematic feasibility and also trajectory tracking with a bounded tracking error. So yeah, this is just to give you an idea of what our methods can do. And yeah, for problems like these, we can generate trajectories in fractions of a second. So for something like this, we can run it in real time, like a model predictive control-like approach. Today, I'm going to first talk about how do we formalize these mission requirements. I'll then introduce what the motion planning problem looks like. By taking a very coarse-grained look at related work, I'll also try to motivate why this is a hard problem. Then I'll introduce the notion of a robustness metric for signal temporal logic that is key to our approach. After that, I'll talk about our first approach, which is called flyby logic. It's a centralized motion planning approach. In fact, the video that you saw was one of the case studies from that. I'll also talk about how can we go beyond just trajectory generation to also having to being able to synthesize controllers that can track these trajectories well. And then we'll try to do all of this in a distributed manner, depending on how much time we have. I'll finally end with some comments about the limitations of these works and talk about ongoing efforts and future directions. So the first question is, like the kind of missions that we saw as specified in the video, how do I capture them in a mathematically sound manner? No surprises there, given the title of the talk, we're going to use signal temporal logic to encode them. So signal temporal logic is a formal behavioral specification language, and it's a logical formula, so its output is a Boolean true or a false, but it's defined over continuous value trajectories. And it's a logical formula that has some elements like, again, I won't go through the full grammar of STL, but I'll just give you some examples. One temporal operator is called the always operator. We usually have that to encode safety. And this says that an event should hold throughout a given interval of time. An example over here is that I have two quad rotors, one unsafe set, and I don't want the quad rotors to crash. What that would mean is that I write a logical formula phi1 that says always, that square over there is the always operator, in a temporal range of 0 to 10 seconds, I do not want the position of quad rotor 1 to be inside the unsafe set. And this notion of a state being in a set or a variable being greater than a threshold is what we call an atomic proposition, or the smallest building block of this behavioral specification language. Similarly, using the logical AND, I can also say that I don't want quad rotor 2 to be inside the unsafe set as well. And I can also encode that I want the distance between these two drones to be always greater than equal to delta. So always is one operator that's going to show up in a lot of our case studies. Another one is the eventually operator, which says that an event should happen at least once in a given time interval. We can use that to encode requirements like that these two drones have to reach a goal set in a bounded amount of time. So over here, I'd write phi2 is the eventually over 10 seconds. And again, the time interval could be anything. I've just used 0 to 10 as an example. I want quad rotor 1 to be inside the goal set. And similarly, I also want quad rotor 2 to be inside the goal set in 10 seconds, within 10 seconds. We can also have if-then type of reactive requirements in signal temporal logic. One example is here, where eventually I want quad rotor 1 to be inside the goal set to imply that it's dropped package P1. Similarly for the second quad rotor. And we can combine these specifications together by either nesting them or using disjunctions or conjunctions. In this case, I just connect them using the logical AND or conjunctions, and I come up with a two-drone package delivery problem or a simplified representation of that. Over here, all the temporal operators had a range of 0 to 10 seconds. So for this case, we can say that we have a specification horizon of 10 seconds. That is, I need trajectories of length 10 seconds before I can say whether or not the specification side was satisfied. In the rest of this work, we'll only deal with problems or specifications that have a bounded horizon. STL, of course, also works with unbounded operators, but that won't be the focus of this work. So with that, we can move on to what the planning problem is. So we've talked about that we formalize the mission requirements using signal temporal logic. And now the problem is, how do I generate trajectories that satisfy this specification? So a little bit more formally, an STL specification is, again, a logical valued formula that takes in my trajectories over all my unmanned aerial vehicles or all my drones, and it's going to map it to a single Boolean true or a false value. True if all parts of the specification are satisfied, otherwise it's false. And then the motion planning problem can be thought of as a finite horizon discrete time control problem, where I take my specification horizon, discretize it. Let's say for these 10 seconds in the previous example, I discretize them at 10 Hertz, so I have 100 time steps. And our problem then is to find a sequence of controls or decision variables for each of these agents such that they satisfy the specification. So that's what this notation in the box is trying to say. Of course, we haven't formalized how, so that's going to be one of the main things that we'll discuss in the rest of this talk. And we want to do this subject to system dynamics and constraints on the system, like bounds on velocity, acceleration, or the thrust that can be applied to these robots. So again, given a STL specification, this is a high-level overview of the type of problem that we want to solve in order to generate these trajectories that satisfy the specification. Of course, we're not the first people to have thought of solving this problem. There's a lot of work that's already been done on it before I even got into the area. So I'll take a very coarse-grained look at some of the related work to see why this is a challenging problem. And again, disclaimer, this is a very coarse and slightly outdated view of the related work. So the most popular class of methods for generating for either control or motion planning with signal temporal logic specifications is to cast the problem into a mixed integer convex form. The idea is to introduce binary variables for atomic propositions or for corresponding to events such as a state is inside a given set or not, and then come up with a mixed integer linear set of constraints such that if you satisfy those constraints, it also means you've satisfied the specification. Two of the papers cited over here have pretty much automatic ways of going from a specification to a mixed integer linear program. These approaches, of course, it's a mixed integer linear program. I think they're double exponential in the number of, essentially the complexity of the formula, so they do not scale very nicely. They also produce what we can call as zero robustness solutions. What I mean by that, I'll try to sketch it out. Right. So imagine I have a mission of the type where I have one unsafe set and I have one goal set that I want my robot to get to. So right now we're talking about zero robustness solutions. Let's say this is where the robot starts off. A lot of these methods generate trajectories that are kind of like discrete trajectories that will be something like this, where they don't really care about what's happening between the samples, or you could have samples that are right at the edge of the unsafe set and still satisfy the specification, and so on. So one of the problems with a lot of these mixed integer programming based methods is that they generate these zero robustness solutions, which need something on top in order to be actually implemented. All right, so that's one class of approaches for solving this problem. The other approach mostly comes from the linear temporal logic side of things, but can also be applied to certain classes of discrete time signal temporal logic specifications. And the idea is, instead of dealing with the continuous dynamics like we did in the mixed integer programming approach, you abstract your dynamics on the workspace. And then based on that discrete abstraction, you essentially turn the problem into one of doing essentially a graph search. The type of dynamics that can work with this are either simplistic, or you lose a lot of the or you come up with plans that are very jagged and need smoothing on top of that. When it comes to talking about signal temporal logic, the type of formula that you can solve the problem for using these approaches are usually a restricted fragment. And these approaches also do not scale well, especially when you add more agents or when you add a third dimension in the workspace, like we do have for aerial robots. So, right. Problem with most of these approaches is that they're combinatorial approaches and they do not scale very well, which is one of the main challenges that we try to overcome with this work. I should also mention that there are other methods that I'm not going to talk about or compare with. For example, you can use reinforcement learning to solve this problem, turns the problem of satisfying an STL specification into one of essentially learning a policy via Q learning. There's also approaches that turn this into a purely convex optimization problem. But a lot of the heavy lifting is done via projections of convex sets, which again do not scale very nicely. There's also great approaches based on control barrier functions, but they both rely on handcrafted barrier functions to some extent and also are restricted to certain fragments of signal temporal logic. So anyway, to overcome some of these limitations, our approach is that we want to go from solving a combinatorial problem, that is, we don't want to solve a mixed integer program or do a graph search, but now we want to solve a continuous problem. In fact, we want to use gradient-based optimizers to be able to solve this problem. And in order to do that, we'll introduce the robustness metric associated with STL specifications. So the robustness of an STL specification was something that was introduced by Yorgos Fenikos and George Pappas in 2009. And while an STL specification, phi in this case, will take in a state trajectory, give you a Boolean outcome, true or false, the robust semantics of STL give you a continuous function rho of phi associated with your specification phi that again takes in the same input, which is your state trajectory over all agents. But now instead of mapping it to a Boolean true or a false, this mapping goes to the extended real line. So you have a continuous valued output. This mapping also has the nice property that if robustness takes on a strictly positive value, it means the underlying specification is satisfied. Otherwise, it's not. So we can interpret robustness as kind of a degree of mission satisfaction. That is, if you generate trajectories that take on a large positive value of robustness, means they can tolerate a lot of disturbances. Whereas if you're close to zero robustness, it means small disturbances can make your system violate the specification. If you have very large negative values, it means you've done a great job of violating the specification, which is also a useful thing, not so much for control, but for falsification. In fact, in Daniel Fremont, you have an expert on that, so I won't get too much into falsification. But anyway, so robustness can be automatically, it's a function that can be automatically generated from a given STL specification. It's nice and continuous, and high values of robustness mean you've done a good job of satisfying the spec. So let's take a quick look at how can we build up this robustness function through one example. I won't go through again the full recursive grammar of building it up. So we'll take an example of a safety specification where I have a robot with a position Q1. And what I want is that always in 10 seconds, I don't want the robot to be inside the unsafe set U1 or inside the unsafe set U2. And let's say I'm given a trajectory of the robot like this for which I want to evaluate robustness. So in this case, the robustness function becomes essentially takes the following form. So it's the minimum over time of the negative max of a sign distance metric that tells me how far away Q1 or the position of the robot is from the unsafe set U1 and the unsafe set U2. Sign distance metric is such that if Q1 is inside the unsafe set, it will take on a positive value. Otherwise, it'll take on a negative value. Corresponding to the negation in the formula, we also have a minus sign in front of the max. And in general, for a discrete time STL specification, where time is not in a continuous interval, but it's over samples, the robustness function consists of the discrete minimum, the discrete maximum, and a distance metric. That's all you need to compute a robustness function. In general, we can build such a function for any STL specification, and we can do it automatically using rules that I'm not going to talk about here today in the interest of time. And it also has the nice interpretation that, for example, let's say for this trajectory, the robustness takes on a value R, which is greater than 0. That means that I can draw a tube of radius R. And again, the tube inherits the shape from whatever distance metric we use around this nominal trajectory. And all trajectories that remain inside this tube of radius R will satisfy the specification. In fact, this tube is more conservative. You could also have trajectories that go outside the tube and still satisfy it. But as you can see, any trajectory that will remain inside this tube is also going to satisfy this particular specification. So just to summarize, what we have now is a robustness metric associated with the STL specification, has a continuous valued output, and can be built automatically following the grammar of STL. So this leaves us then with, well, a very intuitive form of doing motion planning or control with STL robustness, which is, let's just maximize this robustness function, because we know if it takes on positive values, it means you've satisfied the underlying specification. In fact, that is what we do. We maximize robustness, but we had to jump through a few technical hurdles to do that first. The first thing is the discrete min and max operators, of course, are not smooth. As shown in this figure, they have these kinks where the gradient is going to vanish. On the other hand, we want to use gradient-based approaches. The sign distance function is also, in general, not smooth. So if you think about the sign distance to a polyhedron, it's not going to be a smooth function. It's continuous, but not smooth. So again, gradient-based algorithms do not work. One further complication with STL robustness is that it is in general non-convex. So if I have a specification of the reach avoid type where I want to reach a particular set while avoiding a particular set, that leads to a non-convex robustness function. So what we did in some of my older work was we addressed these first three problems and essentially came up with a continuously differentiable, that is a smooth approximation of robustness, which we call the smooth robustness. We did it for metric temporal logic, which is pretty much the same as signal temporal logic for all practical purposes. And it's not only smooth, it also has a bounded approximation error. So we can still reason about whether or not I've satisfied a specification by looking at what value the smooth robustness function takes on. The fact that it's smooth means I can use gradient-based methods to now do the maximization. So that's kind of the key insight behind what we try to do. But there are no questions. I guess I'll move on then to the method where we, sorry.
I have a question.
Yeah, go ahead.
Okay, so can you just go back to your distance measure?
Yeah.
This one. Yeah, can you just, so I said like it's a mean zero, that basically that's you're getting into like a time in that range.
Yes, yeah.
Move along. So there is a minimum, why there is, so the distance is a positive value, right?
Distance is, well, no, so this is sign distance. I should make that clear. It's a sign distance. So it gets negative when you're outside the set. It's positive otherwise.
Okay, got it now. Yeah, okay. So it's a, okay. Thank you. That was,
yeah. Thank you. Yeah, and I should also mention we're looking at discrete time STL specifications. So even though my notation has a continuous minimum, it's really a discrete minimum over samples in time 0 to 10 seconds.
Okay.
And yeah, the sign, the distance is actually a sign distance. In fact, we even look at something much simpler. Instead of looking at an actual distance metric, we just break down our sets into axis-aligned polyhedrons and look at half spaces. So we look at distance to a plane rather than looking at sign distance. But again, I think that's a technicality that maybe doesn't matter too much over here.
Yeah. Thank you.
Yeah. Thank you for the question. All right. So yeah, so we have this robustness function. We have a smooth approximation of it, which we can maximize through gradient-based methods. And that is what we do in our method called flyby logic, which generates trajectories for multi-agent systems in a centralized manner. Flyby logic is a predictive optimization-based motion planning algorithm. It's essentially an optimization for maximizing smooth robustness through waypoint selection. Where again, smooth robustness will be denoted by rho tilde of phi. And smooth robustness again has the property that if I plug in my trajectories into that function, it takes on a positive value greater than some epsilon. It means the underlying specification psi over here is satisfied. And my problem, my optimization is going to be only looking at some coarse-grained waypoints to be selected. So the optimization isn't going to be over low-level controls or over continuous trajectories. It will only be over waypoints. In fact, through this optimization, we ensure that we aim to get two guarantees. One is continuous time satisfaction of the specifications. So even though we deal with these waypoints, which are like orders of seconds apart in time, we still want continuous time satisfaction of whatever's happening between these particular waypoints. We also show kinematic feasibility of the resulting trajectories. So I'll set up this problem. I'll mostly talk about it in the context of a single agent. But if I have multiple robots, I just have copies of the variables and constraints that I'm going to talk about now. So we start off with, again, let's say you're given some initial positions and you're given the workspace that you'll be operating in on the map. The optimization variables for this flyby logic are going to be n+1 waypoints per UAV. These waypoints, P0, P1, P2, and P3 are, again, they're going to be in R3, so they're position waypoints, and they're going to be uniformly apart in time. That is, it takes my robot TF seconds to go from P0 to P1, from P1 to P2, again, it's TF seconds, and so on. And yeah, you can think of TF as, for example, being 1 second if you want to put a number to it. Now, one thing is I have a specification horizon, let's say of H. So even though capital N over here is a design choice, I should pick at least enough waypoints N such that the total flight time is greater than the specification's horizon, so that I can generate a trajectory of enough duration to be able to evaluate the specification. So that's one just design consideration that I should be aware of. Now, just reasoning about these waypoints alone is, of course, not enough. We are talking about satisfying a STL specification, and we want to do that for these trajectories that connect these waypoints. So in order to do that, we're going to restrict the ways in which we can connect these waypoints successively. In fact, the way we do that is by connecting these waypoints via jerk minimizing splines. For multi-rotor aerial robots, these jerk minimizing splines have a very nice closed form expression. In fact, if I'm connecting a waypoint P0 with a waypoint PF, my jerk minimizing spline Q star, in each dimension XYZ of my workspace has the following form for position, velocity, and acceleration. So you can see it's going to be a quintic spline and position, and then derivatives of that for velocity and acceleration. These parameters, alpha, beta, and gamma, turn out to be nice and linear in my variables of interest. So my variables of interest are P0, which is, let's say, a waypoint that the robot is at, the next waypoint PF, the initial velocity of the robot V0, and maybe the initial acceleration and final acceleration. In this particular case, we restrict ourselves to trajectories that have a constant acceleration at the waypoint. So we don't worry about these particular acceleration terms. But long story short, what connecting the waypoints to the jerk minimizing splines does for us is that we have these continuous time trajectories to connect these waypoints as nice linear functions of my variables of interest, and they're parameterized by time, because they're, again, they're splines with quintic, for position, they're quintic splines in T. Similarly, for velocity and acceleration, they're also going to be linear functions of my variables of interest. Now, I want to throw this to an optimizer. So having a continuous trajectory, while it's great for evaluation, it's not good for optimization. So what we're going to do next is essentially, we're going to discretize our continuous trajectories at some high rate, where if TF was 1 second, you can think of the rate, you can think of dt as being 1/20 seconds, or I get samples at 20 hertz. What we're essentially, yeah. So if I have continuous spline connecting P0 to P1, I'll have 20 samples between that. Similarly, I'll have 20 discrete samples between P1 and P2, and so on. And again, leveraging the fact that minimum jerk splines have this nice closed form expression, what this does is that now I have a closed form expression for each of these samples shown by the red stars, or these discrete points along the trajectory. And they're going to be nice linear known functions of the preceding and the succeeding waypoint. And they're parameterized again by which sample they are along the trajectory. So if I have a sample star subscript I, which is between, let's say, P1 and P2, it's purely going to be a function, linear function of P1 and P2, and which sample it is, whether it's the third sample or the fifth sample along this particular trajectory. So through this construction, what we've done is that optimization variables remain very few. We have these just position waypoints, P0, P1, and so on, for each of my capital D UAVs. And then I have a nice linear representation of the jerk minimizing spline trajectory connecting these discretized at a high rate. And through all of this construction, what we've done is we have essentially represented the entire trajectory at a high rate using very few variables. And so this allows me essentially to, if I move my waypoints around, I also know through my closed form linear function, how the resulting trajectory that connects these in discrete time is also going to move around. So that's, again, one of the key constructions that we use in the optimization for fly logic. All right, so yeah, with this now we can talk about the optimization itself. So the optimization then is that we want to maximize the smooth robustness of an STL specification, where the smooth robustness, again, is a continuously differentiable function of these samples of the trajectory that I have. I want to maximize that along the full trajectory. So it's not just the waypoints, it's the waypoints and the red stars, or the higher frequency samples along the jerk minimizing splines, over my optimization variables, which of course are these capital N waypoints for each of the drones. So again, I'm writing this down just for a single drone to keep the indexing simple. But if I had capital D drones, I would have capital D copies of these waypoints. And similarly, the trajectory would also be longer, I guess, or would have more elements to it. So that's the objective over here. The constraints are that we want to do this subject to continuous time kinematic feasibility. That is, I want to generate trajectories such that their velocities and accelerations are within predefined bounds, so that I can say that, a low-level controller will be able to track them nicely. And I want this to hold for all times in my specification horizon. The problem over here is that, of course, if I want to throw this directly to an optimizer, this is an infinite number of constraints. Even if I go about discretizing it and then coming up with a constraint for each of these red stars, that would result in a high number of constraints. It would also be conservative, because I would have to think about what's happening between these samples. So I would have to think about the Lipschitz constant of my spline, and then essentially subtract that from Vmin and Vmax. However, it turns out that for this particular problem, what we could do is that we could find constraints purely on my optimization variables, which are waypoints. And I could find linear constraints on successive waypoints, as shown over here. These functions LB and UB with the subscript V and A for velocity and acceleration are linear functions of the velocities with which we were at these particular waypoints. And then I have these nice linear constraints. In fact, I have very few of them, and they are going to imply that I have continuous time kinematic feasibility. I won't get into the details of that, but it's just, again, exploiting the fact that these jerk minimizing splines have a nice closed form expression. In fact, we have 12 n constraints per UAV to satisfy these continuous time kinematic constraints on velocity and acceleration. On the left is kind of shown a figure that gives you some insight about where the construction comes from. This is saying if I was at a waypoint, it was at the origin, and let's focus on moving along just a single axis. Depending on what velocity V0 I was at that particular waypoint, the corresponding next waypoint that I can pick, or PF, has to lie inside the polyhedron as shown over here in the shaded area. And this essentially comes from looking at the constraints, looking at the intersection of these infinite number of constraints. Turns out we can find a nice closed form, again, linear polyhedron representation of what this constraint set will look like. So yeah, one more thing is we have few optimization variables to deal with, and we have a few linear constraints on top of them. Now, with this particular optimization, we can stop it when the objective reaches a particular threshold epsilon tilde, which is a positive value. And one of the results in our paper was that, one of our papers was that we can pick this epsilon tilde such that it ensures continuous time satisfaction of the SDL specification. So even though I'm doing this robustness maximization on a discrete time trajectory, if the robustness is high enough, it also ensures continuous time satisfaction. And again, it's a simple argument that essentially gives the proof of this corollary. So yeah, one thing to think about is, of course, the robustness is in general a non-convex optimization. So that does keep the problem challenging. But what makes it slightly easier is that we have few variables and very few constraints, which are all linear in our variables of interest. So we can kind of throw this to an off-the-shelf gradient-based optimizer. So put it all together, if you solve this optimization, we first get the guarantee of continuous time satisfaction of the specification, which is one of the things we set out to get. We also have kinematic feasibility of the resulting trajectories. That's just by finding a feasible solution to the optimization. And with that, we can move on to some experimental results to see how this optimization works. As a first problem, we'll look at a multi-UAV reach avoid problem, where I have to always avoid an unsafe set. My UAVs, there's capital D of them, have to reach the goal set within a given time interval. That's 0 to 8 seconds in this case. And the UAV should also be at least 0.2 meters apart from each other, so they're not crashing into each other. I can write this down as the following STL specification using just the always and the eventually operator. And then we can essentially use all the construction and flyby logic. And what we have over here is an experiment with 8 crazy fly quadrotors. I think in this case, the horizon of the specification is just 6 seconds. On the video is kind of low resolution. It'll play at a slightly higher resolution than the screenshot over here. But you have a goal set, which is on the far side of the room. So the picture-in-picture is not aligned with the actual axis of the workspace. You have a large unsafe set in the middle, and we have 8 drones that have to visit this goal set. All of them have to do that within 6 seconds. Through our method, we can indeed generate trajectories where you see that all of the robots make it inside the goal set, then they head out, letting the others enter. And the fact that they're trying to go as deep inside the set as possible while staying far away from the unsafe set is because they're trying to maximize robustness. So we're not getting these zero robustness trajectories where they touch the edge of the unsafe set or just touch the edge of the goal set. One of our main motivations was to come up with a computationally tractable method. So even if it's a non-convex optimization, we see that it scales nicely as you increase the number of drones. The amount of time that it takes you to find a satisfying solution looks like it's scaling almost linearly with the number of drones. The problem still, of course, is NP hard. So this is just more of an empirical artifact of the kind of method we have employed. The mixed integer linear programming based approach, Blue Steel, is very fast when you have one drone, but as you start to add more agents, it scales very poorly. So the other, it does work for up to 6 drones, but I'm not going to show those results over here. Yeah, one thing we noticed was that, of course, as you plan together for all of these agents, you do see a slowdown or how much in your compute time. So we also, it's kind of motivates why we want to do this in a decentralized manner, which we'll talk about later. We also implemented all of this in a C++ library with an easy to use API, the code for which you can find on this link over here. And it is at least 1 order of magnitude faster than the results in the previous slide. We're not just limited to reach-or-wide problems. We can handle the full grammar of STL. And this is one example where we use the until operator in signal temporal logic. So over here, we do the planning in R2. We have 4 robots shown over here. We have one moving unsafe set, which is shown with the red ellipse. And we have 5 static unsafe sets, which are these red boxes. These robots have to all reach the goal set without crashing into each other, without crashing into the moving obstacle or the static ones. And the additional requirement is that this robot in blue should not get into the goal set until the robot in pink does. So for something like this, again, we can throw it to flyby logic, and it generates the following trajectories. So you see that first 2 robots made it in. The pink robot then makes it in to the goal set, which is in green, before the blue robot does. Has this, the optimization naturally generates this interesting loiter-like pattern for the blue robot, where it picks these 3 waypoints close to each other and just like essentially flies a time-wasting pattern while making sure it's staying far away from all the other agents. And yeah, so this is again, flyby logic can handle the full grammar of STL. One thing I should point out is that one limitation is that we, of course, need to know what the moving obstacle is doing perfectly a priori. Otherwise, we can't apply our method. Oh, sorry, and PowerPoint crashed with that. Sorry, just give me 1 minute and let me get back to where I was. I hope you can still see my screen.
Yes.
Great. Yeah, okay. Sorry about that. So yeah, we talked about flyby logic, which generates trajectories. Next, we want to go design the motion planner and a tracking controller so that you can track these trajectories with a bounded tracking error. This is work that was published in ACC 2021 and was done jointly with folks at the University of California at Berkeley. The idea is that we want to have a following core design architecture where we use flyby logic as the trajectory planner. So it's going to take in the STL spec, the UAV kinematics and the kinematic constraints. It's going to generate trajectories, but it's going to take in an additional input, which is this dashed line going from a tracking controller that tells you about the worst case tracking error. So the trajectory planner is going to be aware of the worst case tracking error of a controller. We'll also synthesize a possibly nonlinear feedback controller that accounts for the full nonlinear UAV dynamics and also respects state and input constraints. Yeah, and one more point is we have a proof of bounded tracking error with this as well. So that's the third thing that it's going to do. The first component, again, is flyby logic, which we can think of as doing motion planning in the kinematic space, or through generating these jerk minimizing trajectories, we're essentially finding a solution with the following kinematic model, where the states are positions, velocities, and accelerations, and the inputs are jerks in the 3-dimensional space, X, Y, Z. The second component is a robust trajectory tracking controller that takes into account nonlinear UAV dynamics. So it has 8 states. It's a nonlinear function with the simplification that we set the yaw and its derivatives to be 0. So this is going to take in, again, a controller that's going to take in the UAV kinematics, the UAV dynamics as well. And it's going to use that to compute the error dynamics, where the error E is the dynamic state X minus a mapping of the kinematic state X hat through this matrix G. And with that, for this particular system, the error dynamics E dot turn out to be, they're nonlinear, but they're at least control affine, which allows us to use existing approaches for controller generation. And we'll in fact synthesize a controller that minimizes the tracking error subject to input constraints or constraints on state U. Constraints on the input U. The constraints on the state are taken into account by the kinematic constraints anyway, so we don't need to worry about them too much. One of the key contributions of this work is to synthesize this robust controller that can do all of this. And the way we do it is by solving a sum of squares optimization. I don't have time to get into the details of that. But the guarantees of this construction or the synthesis is that we can find a nonlinear feedback control law, K of E, where we have actually an ellipsoidal bound on the worst case tracking error, which also can be turned into a hyperrectangular bound, or well, infinite norm bound as shown over here. And it also has guarantees that the control value will be within its predefined values. This particular control bound delta is something that can feed in as an input to the flyby logic optimization, which we slightly modify to also take into account the jerk kinematic constraint, so that now the jerk is also going to be bounded, which we did not have in the previous formulation. And we want our smooth robustness value to be greater than a threshold that includes our worst case tracking error in there. The main result is that if you can actually solve the non-convex optimization and get a high enough objective value, it means you have satisfied the specification in continuous time. And with your controller KE, you won't have a tracking error that's going to make you violate either your constraints or your specification. The overall planning and control architecture is going to look like this, where we have a centralized trajectory generator. You have your tracking controller, which is nonlinear feedback law via sum of squares, and that can feed in to an off-the-shelf attitude controller for these UAVs. I guess I'll go over one case study where we have 4 UAVs, and think of them as doing 2 missions each, and again, teams of 2 each. UAVs 1 and 2 have to cycle between zones 1 and 2 every 10 seconds. Oh, sorry, every 5 seconds. UAVs 3 and 4 should visit a delivery region, which is in green, the first 10 seconds, then go to the base of the next 10 seconds. They should do this while, of course, not crashing into each other, while avoiding an unsafe set, and so on. And so I can represent this mission in the following specification. It's not as bad as it looks. It's actually a relatively straightforward specification. And then using our co-design approach, we can both generate trajectories and track them such that you satisfy the specification by using the full nonlinear dynamics of the UAVs. So I have essentially 2 3D views and the top-down view. In red, we have the actual trajectory. The red dot is showing the next state that the controller is trying to track, or the reference for the controller. The ellipsoid, of course, is the worst case tracking bound. It's being updated in real time over here as a function of the error state. And you see that you do indeed have 2 robots that are circling between these yellow sets without crashing into each other. The other 2 are going to go inside the green set and then go inside the the light blue set, which you can barely see. We wanted to guarantee that our tracking error is going to be within bounds. Turns out that is indeed the case. In fact, this also shows that our worst case tracking error is pretty conservative. But we see that both for velocity and tracking, our errors are going to be within bounds. We focus on one particular UAV over here. And these worst case tracking error is less than the bounds introduced by the robustness. So as long as you track within your desired bounds, you also will end up satisfying the STL specification. So that's one more thing about this. I guess I'll briefly in the last 5 minutes talk about the distributed trajectory planning approach. I'll skip the details of that. The idea again is the same as flyby logic. You have this optimization over waypoints for these robots. You want to maximize the smooth robustness subject to these constraints. But now you want to do this in a distributed manner where each robot or group of robots is making their own decision, while being, of course, communicating with each other and being cooperative. So the high-level idea is that we're going to divide our entire fleet of robots into groups. Each group or each UAV in a group is in parallel going to solve convex subproblems that are associated with the with maximizing the robustness. And the groups are going to communicate the solution with each other, and they're going to repeat this process until convergence. There's different ways in which these groups can choose which group goes first in the algorithm and so on. But yeah, the details are formalized in the paper. I won't talk about that too much, I guess, in the interest of time. I'm going to skip the details over here, but on the inside, we're solving actually a nice quadratic program that kind of corresponds to doing log coordinate gradient ascent on the smooth robustness of STL. These block coordinates are essentially the variables associated with a particular UAV. So it's like you go in one direction in the space associated with the variables of one UAV, then you move on to another UAV, go in the other direction associated with its variables, and so on. Anyway, you can skip these particular details. But one of the main guarantees is that this algorithm is going to converge to a stationary point on the smooth robustness, which again may not sound like much. That's just converging to a stationary point doesn't really give you any strong guarantees. But even having convergence for a distributed algorithm that can handle the full grammar of STL, our work was the first that actually did this. Second guarantee is again that if the algorithm converges to a stationary point with a high enough STL robustness value, then it means you have generated trajectories that satisfy the spec and are also kinematically feasible. In fact, you can also combine this with the controller through the core design process and get dynamic feasibility or bounded tracking error as well. I guess we'll again use the same reach-avoid problem for benchmarking. There's capital D UAVs. They have to get inside a goal set within a bounded amount of time, avoiding each other and the unsafe set. And I guess here's a simulation with 4 UAVs that just tells you that, the distributed approach can also generate trajectories that satisfy the specification. No surprises there, otherwise I wouldn't be talking about this. But the interesting thing is when we do a comparison of this to the centralized flyby logic approach. So we're going to do this with increasing number of UAVs going from 2 to 8. And first is we look at the amount of time that it takes to find a satisfying solution or a set of trajectories that satisfy the underlying STL spec. Turns out that on average, the distributed approach is faster. When you also let it run to convergence, the distributed approach is faster as well, but this doesn't actually mean much because it turns out when you look at the actual robustness values that were obtained from these trajectories, and again, with robustness values, higher is better. It turns out that the centralized approach is doing better. And in fact, if you look at the papers and their convergence theorems for either of these and compare them, it's not a surprising result because you do expect better convergence for the centralized approach. So the takeaway is that centralized optimization does do better in terms of robustness, but the distributed one is faster. And again, it can handle the full grammar of STL. Over here, we have a reach-avoid problem where one drone should not get to the goal set until the other goal does, until the other drone does. I'm going to skip the simulation in the interest of time. We can also nest operators. We can have an eventually always or an always eventually operator as long as you have a bounded horizon for the specification. And our method can also solve for that. Again, I'm going to skip that. I guess I'll conclude by talking about essentially the summary of what we have done in this particular area, what ongoing and future work is going to look like. So to summarize, we proposed this flyby logic, which is first we actually proposed a paper called Smooth Operator, which looked at a continuously differentiable version of robustness for metric temporal logic specifications. Also had bounded approximation error that enables all of this to happen. Through flyby logic, we propose a centralized trajectory generation scheme for multi-UAV systems with signal temporal logic objectives. If you want to do all of this with some other types of dynamics, you can actually do that for direct dynamic control by using just the smooth robustness function. So it's not just restricted to multi-rotor UAVs, but that's the case when we have the most efficient formulations. We also came up with a distributed approach called flyby distributed logic that has some nice convergence guarantees and again works for the full grammar of STL or allows you to express a wide variety of requirements. Both these methods generate kinematically feasible trajectories. And in fact, through a core design approach, which works with either flyby logic or the distributed version, we also have guarantees on bounded tracking error through synthesizing feedback controllers. Simulation results and comparisons to other approaches show that the approach does work well. It's computationally fast. But I should, of course, point out this is not a silver bullet. There are a bunch of limitations. The largest one, in my opinion, is that these are not complete algorithms. That is, even if a trajectory exists that will satisfy the STL specification, there is no guarantee that our methods will find them. Well, of course, that's because we're solving a non-convex optimization, and we want the objective to be high enough. One way to mitigate that in practice is by doing a multi-start or by having multiple initial guesses of trajectories and then doing gradient-based approaches starting from those initial guesses. But again, that doesn't quite get around the fact that we do not have completeness. Another is that the correctness of the generated trajectories depends on knowing the environment perfectly and all the uncontrolled agents in it being perfectly known a priori. So you need to know from time 0 till the end of your specification horizon what everyone else is going to do in the specification, is going to do in the environment, which again makes life, it makes this kind of hard to apply in some realistic settings. The convergence again kind of ties to point 1 that these are not complete algorithms essentially. Second, the final limitation is that the distributed approach requires a fully connected network and assumes perfect communication. Some of the ongoing work is on overcoming these limitations. First is to kind of focus on the case where system dynamics are partially known. So we're looking at the case where you can essentially come up with a data-driven representation of the part of the system dynamics that you do not know. So we're using Gaussian processes and Bayesian linear regression. And then how can you still generate plans that satisfy the STL specification with high probability? We're also looking at problems where the environment is uncertain and only partially known, as opposed to all the examples that you saw here. On the distributed side, we are trying to explicitly encode a couple of communication requirements. One is line of sight between certain agents in the entire fleet. And also, we're trying to take into account fading, or that we want the robots to be in areas where the communication is reliable. Finally, we're also trying to look at what are useful fragments of signal temporal logic for which we can prove completeness. Again, I would say useful and non-trivial fragments of STL for which we can prove completeness. And that's one more area that we're looking at. And before I conclude, I should say there's a lot of work that has been done by other folks that builds on top of, for example, finding smooth robustness. And people have come up with very interesting work also using control barrier functions, combining SAT solvers and optimization. And I think more recently also using like graph convex search for controller synthesis, which of course, all of this work kind of predates that. So yeah, with that, I'll conclude the presentation. And yeah, thank you for your time and attention. If you have any questions, I guess we have a few minutes for that. Thank you.
Okay, so are there any questions? Yes.
Hi, thank you for this very nice presentation.
Thank you.
I have a question about the robustness metrics you're using.
Mm-hmm.
I understand that you are trying to like find a good corridor along kind of away, find a trajectory that is away from all the obstacles as much as possible intuitively, right?
If I have a safety specification, then yes, that's kind of the takeaway. But as you see in these other specifications, sometimes it's not just safety. There's a lot more than safety that goes into STL. So yeah. But anyway, go ahead.
Yeah. But my question is like, I think the robustness that we you consider in this presentation focus on the errors when you are flying, during the flight from one position to the other. Mm-hmm. But I'm actually thinking if there is any other additional consideration about robustness on the logics. For example, like when you have, for a simple example, like when you have two drones and one drone will fly to a target set after the other fly away. Mm-hmm. But what happened when let's say the other target set, let's say Q2 actually fly away and back and away and back. It's more like, can you provide more insights about like the robustness on the logics rather than the fly?
Okay, I think I get your question. And I think the key takeaway, which maybe I did not explain very well, is that this robustness is actually associated with the temporal logic specification itself. So even though I gave you an example where it's just a safety specification and you can think of it as tracking errors being bounded, that's not the only thing that this robustness is for. In fact, for all the examples where we had UAVs, for example, you have this precedence between UAVs that one UAV has to get to a goal set first, or in these type of examples as well, this entire specification has an associated robustness function with it. And it's that robustness that we're trying to maximize. So it's not just in space. So it's not just saying that I want to be very far away from the obstacles. It kind of also means that the robots should satisfy all of these behaviors in the most robust ways. For example, get as deep into the deliver set as possible or get as deep into zone 1 as possible, essentially hit the middle of these rectangles. And so, yeah, I mean, the robustness is not just for obstacles, it's for the full specification. I don't know if I hope that kind of helps the understanding behind it.
I have a question. So this is really just a talk. Thank you for it. It seems like the smooth robustness function seems very similar to barrier function. Does it act as a barrier function, or is there some distinction?
There is a distinction. The first thing is that the smooth robustness function takes on the full trajectory, whereas barrier functions are usually state-based.
Okay.
So that's like, I think, the biggest, just in the functional form of it. But of course, people have looked at using barrier functions to generate controllers that satisfy STL specs. But the form they take is like, again, I don't know if there's a direct one-to-one relation of that with smooth robustness that I know of. Maybe there is, it's just, yeah, I'm not directly aware of that. But an interesting thought, nevertheless.
Daniel had his hand up on the Zoom.
Yes. Yeah.
I did, but do we have time?
Yeah, sure.
Yeah.
Okay, thanks. Thanks, Yash, for the very interesting talk. I would just wanted to ask a bit more about, you mentioned you're looking at an extension more into like the reactive synthesis kind of setting where you don't have, the environment might be adversarial, you don't know what it's going to do ahead of time.
Yeah.
So if I remember correctly, some of the older approaches you mentioned at the beginning allow at least a limited form of that, where you know something like the environment has to fall within some set rather than knowing exactly what it is. Does your optimization approach allow that kind of setting too?
Directly, no, it does not. But one thing is that through robustness, we kind of, again, have some type of robustness to some changes in the environment. Because again, the robustness can be interpreted as being like a tube around your trajectories in space for most specifications. So there is some built-in robustness via that. Those other approaches that you kind of talked about, they're mostly looking at like assume guarantee like synthesis, right? So they're restricted in the types of discrete STL specifications that they can handle naturally, because they're doing that over LTL specs actually. But yeah, I haven't quite thought about how to make this similar to that. But what we're looking at is essentially framing. Again, we're kind of trying to go into a chance constrained optimization type of a framework where you make some assumptions about, not about that the environment is going to lie in a set, but maybe it has some nominal behavior with a lot of uncertainty around that. So how do you account for that? That's kind of like the immediate step that we're taking right now.
Thanks.
Yeah, thank you.
Any other questions?
I have another question. So for the waypoint generation, is that something that's only done offline, or can you do that in real time as the system progresses?
You can do that in real time as the system progresses, subject to your specification not being very complicated.
Okay.
Because the more complicated your specification, the harder the optimization. In fact, I don't have results in this particular presentation, but we do have work where we show that for simple reach avoid problems, we can definitely do this online. And again, the waypoint problem doesn't need to be solved very quickly because these waypoints are like, say, 1 second apart. So we can definitely run this at like 2 or 3 hertz as an online shrinking horizon optimization, kind of similar to receding horizon and MPC. But again, with the caveat that the specification shouldn't be too complicated.
I have another question about, I think you are saying that it's not computed very necessary. I mean, I just want to know, like, the other for zone like 1, the Q1, do the other zones like Q2, Q3, Q4 be considered as unsafe state in the simulation?
Oh no, so we're doing this planning, at least in most of these cases, in a centralized manner. So what that means is I'm planning for all the drones jointly. So my optimization variables are the waypoints for drone 1, the waypoints for drone 2, the waypoints for drone 3, waypoints for drone 4. And I'm doing this optimization jointly in a way that it satisfies my specification. So I don't need to treat them as unsafe sets, but yeah, the underlying specification is kind of, I guess the last line in here, I don't know if you can see my pointer, but what this says is that pairwise, all of the drones should be like 0.2 meters away from each other always. So this turns into, again, a part of my non-convex objective through the robustness function.
I'll have one question.
Yeah.
So in these problems, similar like like when you solve the problems on a graph, like finding the shortest path problem is well defined, but finding the longest path problem is less well defined. So I want to ask you, for example, in these solutions, I feel like there is a problem, like in principle, a problem. Like when the time constraints are very different in the magnitude. For example, 3 drones can, for example, quickly get to their target, but they have to wait to another one, which take long time. So
yeah.
While this happens, those 3 drones should somehow hang around somewhere and simultaneously avoid obstacles. So since like I think in your simulation you have one very good trajectory if you can go there to where one drone do some like there is like a needle type of the trajectory going there and back. And I just could imagine if have to wait even more, we'll probably do some even more going back and forth whatever doing. So what did you see in your work? How your solution handled that? Is there like some great breaking point where actually you cannot get solution because of just a huge disparity in the times constraints?
Yeah, that's a very interesting question. I haven't thought about what it would take to, again, it's a non-convex optimization, so I'm sure it wouldn't take a lot to break. And if in terms of robustness, having a huge disparity in times, at least numerically, it shouldn't be a big problem for gradient-based methods. But like, one kind of quick fix to generating trajectories like this is, and we tried this, but we lose all correctness guarantees after that, is to have an objective that is not just maximizing the robustness, but also minimize some lambda times the path length. So if we do that, we end up with very well-behaved trajectories as opposed to these. But then you kind of, your objective is now trading off satisfying the STL spec with finding short like path lengths. So it doesn't necessarily always find satisfying specs. So I did not talk about those results here.
Can the, like, because all your robots move, can you have like a stopping state, like you can stop and then handle that way?
That's an interesting thought, and I think it would be more feasible in a method that's like you came from the graph-based approach, right? So for approaches that maybe look at this from an automata-based solution, those might probably incorporate that more naturally. In this case, again, it's a continuous optimization, so it's very hard to kind of introduce the stop state without, again, introducing integer variables. And that's one thing that we really wanted to avoid to make this fast.
It's a very interesting talk. I have more things to ask you, but I will save that for the those details to our in person.
Awesome. Yeah. Thank you.
Very interesting talk. Yeah.
Thank you, Dejan. Thank you, everyone, again, for all the questions and for your time.
Okay. Well, if that's all, well, we can then.